Hello and welcome to the WindowsSCOPE Student Series tutorial on 64-bit virtual memory management. In this tutorial, we will walk through a few of the differences between the 32 and 64-bit virtual memory management. As you can see here, we are running a 64-bit operating system. This means addresses can be physically implemented with up to 64 bits. We can use WindowsSCOPE to see examples of 64-bit addresses. This is easily accomplished. If we go to any process and select Code, we will see the addresses are now 16 nibbles long. An address of this size allows you to address 16 exabytes of virtual memory. Since current machines are not close to requiring support for this much memory, current hardware implementations use only 12 nibbles and require the first 4 nibbles to be set the same as the valid bit. This allows Windows to allocate up to 16 terabytes of virtual memory. Unlike x86 systems, which divided their virtual address space into two parts, the 64-bit address space is divided into a number of different size regions. User applications still get the bottom half, up to 00007 FFF, and system applications get the top half, starting with FFFF8 followed by 12 zeros. As you can see, all of these addresses are located in the bottom half of memory. If you would like to see an address which is part of system memory, we can do this by selecting a driver. Drivers are located under the system space, so we will be able to see that any of them will start with 4 Fs and a hexadecimal value higher than 8 in the 5th digit. As newer processors support more of the addressing bits, the lower half of memory will expand upwards, towards 7 followed by all Fs, while the upper half of memory will expand downward, towards 8 followed by all zeros. If you would like to see the page where this virtual address is pointing to, you can translate the address given. The only thing you need to do is expand the hexadecimal values and translate each section to a new hexadecimal value according to this convention. By right-clicking on the instruction and clicking Look Up Page Table Entry, WindowsSCOPE automatically translates the address for you and takes you directly to the page you desire. As you can see, WindowsSCOPE has organized the page table to make each entry easily accessible with any virtual address. You can see some of the most important memory management structures like the page map, page directory pointer, page directory, and page tables. On the pane to the right, you will see the virtual page which lists every bit on the table and describes what each bit is used for. For example, the NX bit flags pages which contain data as non-executable. For more details on what each bit does, you can reference the 32-bit virtual memory management video. If you would like to see how the operating system handles a memory management function, you can do this by going into IE Frame, an Internet Explorer browser user interface library. This library exports many functions needed in order to run your browser, including memory management functions. I have selected this node, which as you can see makes a call to two very important virtual memory functions, virtual query and virtual alloc. Virtual query provides information about a region of consecutive pages beginning at a specified address. The function determines the attributes of the first page in the region and then scans subsequent pages until it scans the entire range of pages or until it encounters a page with a non-matching set of attributes. It then returns the status of the scanned memory and the size of it. For example, in this case, you can see virtual query is called and a comparison is occurring. If the program determines it needs more memory, the function virtual alloc is called. If not, this jump will occur and the function virtual alloc will be skipped. We will follow the function virtual alloc in order to understand how virtual memory is allocated. The first thing we need to do is find out where this function is coming from. We accomplish this by going to the import address table and finding the address or the function name. Here we see this function is being imported from kernel 32, a library which redirects function calls through the library kernel base in Windows Vista and newer versions. The library kernel 32 was used in previous versions of Windows and was kept in order to support backwards compatibility. We will go directly to kernel base and graph it in order to see what happens when the function virtual alloc is called. You can see kernel base contains many functions related to virtual memory, such as virtual alloc ex a function which reserves or commits a region of pages in the virtual address of any specified process. The function we are following, virtualalloc, reserves or commits a region of pages in the virtual address space of the calling process, in our case, Internet Explorer. From the graph, you can see some operations are performed, and there are two possible calls which can be performed: nt-allocate virtual memory, or rtl restore last win32 error. Since we are interested in the functionality of virtual memory, we will follow nt-allocate virtual memory. In order to see where this function is going, we need to find it in the IAT for this library. On this IAT, we can see nt-allocate virtual memory is coming from the library ntdll at this target address. In order to see the code, we need to go to the disassembled view and find the address, or by going to the function name under the graph view. Here you can see the EAX register is loaded with the hexadecimal number 15 and a system call is performed. A syscall is a fast call to privileged level 0 system procedures. In Windows, all system calls are handled by the System Service Dispatcher, which indexes the SSDT. We can see the SSDT under OS Structures, and if we look at entry 15 hex or 21 decimal, we will see our function, nt-allocate virtual memory, its target module, NTOS kernel, and its target address. We can find NTOS kernel under the driver's view. And by going to its disassembled view, we can see the code which is performed in order to allocate virtual memory. You will notice here that operands have different names. The names which start with R correspond to registers which hold 64 bits of information. The ones which start with E access the lower 32 bits of information. Registers without the prefixes R or E access the lower 16 bits of information. In Windows x64, the register RCX, RDX, R8, and R9 are used for integer and pointer arguments. Here you can see the kernel is accessing those registers to get the arguments it needs, and it will perform the code necessary in order to allocate the virtual memory requested. For example, you can see this is performing a few pushes onto the stack, and once you scroll down, you can see those same registers are going to be popped, and eventually the function will return back to the caller. This concludes our introduction video to 64-bit virtual memory management. Thank you for watching, and please watch our other tutorials.